I know there was at least one person who was a little confused about the assignment that I put up on D2L. I put an assignment up on Thursday that said September 6th and September 10th and gave a couple of problems to do. But those aren't, when I put those dates up, those are like supposed to be the days that they're like assigned, you know? So we haven't done that stuff yet. We'll do that stuff today. So if you looked at those 4 problems and a lot of it seemed confusing, it'll make a lot more sense after today. That was, the day class didn't have a day off and we had the Monday off. So now we're like one class behind them. That's how this all works. Do you have lab this week? And you can go to either lab, whichever one works for you. All right. So what we've talked about so far, we're working our way through this. So we're working through the kinematic variables. We talked about position. I'm going to break it up like this. The variables that we're going to use have directional information included in them. The way it's included in one-dimensional motion is the sign. The sign tells you, positive refers to one direction and negative refers to the other direction. But we're more used to just in everyday speech talking about non-directional quantities. And everything that we talk about physics has sort of an everyday speech way of being referred to using non-directional stuff. So I want to make the connection between the directional quantities that we're going to use and the non-directional quantities that you're more used to hearing about. So the first thing we talked about is the position. We went through the definition of position last time, Wednesday. That has a direction associated with it because position can be positive or negative. So the sign of the position tells you whether the object is on the positive or negative sign of whatever you're calling your zero, the reference point. And there's no real equivalent, non-directional equivalent position. But all these other ones are going to have. So this we've done. But the next thing I want to talk about is displacement. I'll write that as a lowercase d. And that is very closely related to distance. And we're pretty used to talking about distances. And then after that, I'll talk about velocity, lowercase v, and the velocity does have a sign associated with it, a direction associated with it, but it's related to speed, which doesn't. If you're driving to Iowa and back, your car tells you you're going 60 miles an hour no matter which direction you're going in. Velocity, that's not the case. Once you decide what your positive direction is, one of those ways would say your velocity would be positive 60 and the other would be negative 60. So that's the way the direction's associated. And then the last one is acceleration. I'll write that as a lowercase a. And we still talk about acceleration in everyday speech, but we kind of break things up into acceleration you think of as speeding up for the most part, and deceleration you think of as slowing down. Our acceleration is going to include both of those two things. And right now we're talking about one-dimensional motion. In one-dimensional motion, acceleration means either speeding up or slowing down. But we're going to see when we get to 2D, and if you went on to 3D, which we're not doing in this class, but in both of those, acceleration doesn't have to be associated with speeding up or slowing down. You can have a big acceleration even if the speed is constant if you're turning. So when we get to 2D, acceleration will also be associated with turning in addition to speeding up and slowing down. Okay, so we're on this one, displacement and distance. Okay, so first let me just define displacement. So consider two instants. The first one we'll call T1 and the second one T2. So those are just the times associated with these two instants. This is the earlier one. And this is the later one. Then the displacement T1 to T2 and we'll call it D is equal to the position at time 2 minus the position at time 1. That's one way to write it. Another way to write it would be if you think of the position as a function of time, then it's the position at the time T2 minus the position at the time T1. So you can think of it as position at the later instant minus the position at the earlier instant. Is there a sign associated with displacement? Well, it was in the directional column up here. So that means that, since sign is the only way we have in 1D to represent direction, displacement must have direction associated with it. And what that sign means is which direction overall the object is moved from instant 1 to the, from the starting instant to the later instant. So notice the sign gives the overall direction the object has moved between T1 and T2. So if the displacement is positive, it means that the object between those two instants has overall moved in the positive direction, whatever you're calling the positive direction. And if it's negative, it means the object's moved in the negative direction. Anybody have any questions yet about that? Yes. Yeah. Okay, so excuse me. The next thing I'm going to do is just do an example problem, and we're going to incorporate displacement into the calculation. Okay, so say we have a cliff with a little ledge there. I guess another little ledge there, and then the water down here. And there's a beam coming off the top of the cliff, and a person standing on the beam. In a bathing suit, just in case, though. And that's a bungee. Okay, this person, that bungee's too long. Don't go bungee jumping with a rope as long as the distance to the water. Okay, that's better. And okay, let's say that the distance from the ledge to that first little cliff is 2 meters. Between the two cliffs is 5 meters, and then 3 meters down to the water. And the bungee jumper jumps from the beam, and 2 seconds later exactly touches the water. So he's not injured. And 2 seconds after that, he reaches the point A. That's this. And 2 seconds later, he reaches the point B. And we want to draw a graph of the position versus time. And in order to do that, we have to choose our 0 position, our positive direction, and when the time is equal to 0. Let's say the 0 position, question? Oh, I meant it. Okay, so the 0 position is at point A. Positive direction is up. And 0 time is when he jumps. And then the second one is we want to calculate the displacement from, let's say, time equals 2 seconds to time equals 4 seconds. Okay, and then let's do one more. What's the displacement from time equals 4 seconds to time equals 6 seconds? Anybody have any questions about just imagining what's happening? All right, so the first thing I'm going to do is just give sort of a diagram of the motion. I did this on the other examples similar to this that I've done so far. So there's the top. There's the point A. There's the point B. There's the water. And before we even start thinking about the numerical labels for these different points, we can think about the motion. So the person starts at the top, goes down to the water, bounces back up to A, and then the end of this motion is at B. And now we can start to think about the numeric labels that go on these different points. So let's first do the times. Okay, our 0 time is right when the person jumps, so the numeric label here is 0 seconds. 2 seconds later than that, the person touches the water, so this point here has a time label of 2 seconds. 2 seconds after that, the person's up at point A, so what would the time label be at this point? 4, yep. And then 2 seconds later, they're at B, so this is 6 seconds. Now let's think about position labels. What are we calling 0 position? A, so this is 0. And we're saying positive is up. So what would be the position label at the top? The distance between these is 2 meters. So if you start at 0 and go 2 meters in the positive direction, what's the label? Positive 2. And now for B, the distance between these two is 3 meters. So if you go 3 meters, you start at 0 and go 3 meters in the negative direction, where are you? Negative 3. Oh, you're right. You're right. It is. Yeah, this one's 3 meters. This one's 5 meters. So you start at 0, go 5 meters in the negative direction. So this is negative 5. Okay, so this is negative 5. And now starting at negative 5, you go 3 meters in the negative direction. So what's this? Negative 8. Anybody have any questions about those? Yes.
I don't understand how you go from positive to negative 5. How did you get
Okay.
positive 2?
Well, we know that we know that the distance between these 2 points is 2 meters. And between these two is 5 meters. And between these two is 3 meters. So if you start at 0 and you go in the positive direction, the numbers go up. If you go in the negative direction, they go down. This was where we chose the 0. So if you start at the 0 and go 2 meters in the positive direction, you're at positive 2. If you start at 0 and go 5 meters in the negative direction, you're at negative 5. So it's always pretty easy if you start at 0, you know. Because however far you go, that's the absolute value of the number. You just have a positive if you went in that direction or a negative if you went in that direction. And then from here, at B, we're at negative 5. And we're going to either add or subtract 3 meters from that, depending on whether we go positive or negative. We went negative, and so negative 5 minus 3 is negative 8. Any other questions? Okay, so now I'm going to write out that table. So position, time and position values at all those points now. At the start, time is 0 and the position is 2 meters. 2 seconds after that, we're at the time 2 seconds and the position negative 8 meters. 2 seconds after that, we're at time 4 seconds and position 0. And then the last one, time is 6 seconds and position is negative 5 meters. And now to go from this table to graphing it, you're just plotting those points. So let's see. The horizontal is always the time. The vertical is always the position. The times we care about are 2 seconds, 4 seconds, 6, 8. Oh, only 4, only 6. And then the positions, we have positive 2 meters, negative 5 meters, and negative 8 meters. The first point we have to plot is 0 time 2 position. So 0 time 2. And then the next one is for time 2 seconds, for position negative 8. The next one is 4 seconds, position 0. And then the last one is time 6 seconds, position negative 5. And you can just draw straight lines between those, but it would look something like that if you really measured where and when, the person was through that whole motion. Any questions about that? Okay, so we've done a couple examples like that already, but now we're going to do the displacement calculations. So part B, we want to figure out the displacement from time equals 2 seconds to time equals 4 seconds. So that displacement is just going to be equal to the position at time 4 seconds, the position of the later instant of the two that are relevant, minus the position at the time 2 seconds. And we can just get these off the table. So at 4 seconds, what's the position? 0. And when time is 2 seconds, what's the position? -8. We have 0 minus -8. And so the displacement is positive 8 meters. Okay, so between those two instants, distance person has, well, I should be careful. So at those two instants, person is at two different spots, right? The distance between those spots is the absolute value of this. In this case, it's 8. And the sign of the displacement tells you whether the person has gone overall in the positive or negative direction. So in this case, the person has gone in the positive direction 8 meters because they started here. Let me look at the other one instead. So they started down here at the water and ended up at that point. Okay. So now let's do the same thing, but we want to do it from time 4 seconds to time 6 seconds. Okay, so let's look at the picture and predict what we're going to see. So for this interval, the person starts up here and ends up down here. It's 5 meters between those 2 points. So we expect the absolute value to be 5. And does the person go in the positive or negative direction? Negative. So we expect that answer to be -5. And that's what we're going to get when we subtract. Okay, so the displacement is the position at 6 seconds minus the position at 4 seconds. So that is -5 meters minus 0, and you get -5 meters. Any questions about that? Okay, so now, what if you wanted to calculate, let's do 2 more. So now let's say what's a displacement from time equals 0 to time equals 6 seconds. And then we'll do the same thing with distance. So what's the distance traveled from 0 seconds to 6 seconds? Okay, so the displacement, we do the same way that we did before. So the displacement is equal to the position at 6 seconds, -5, So -5 meters minus the position at 0 seconds, which was +2 meters. And you get -7 meters. So, and the negative says that you've gone the net, like between the point here and the point here, you've gone, there's a distance of 7 meters between those 2 points, and that it's in the negative direction. But when we calculate the total distance traveled, it's not going to be +7. In the other cases, it would have just been the absolute value of the displacement that we calculated. But now for the distance, the way you have to think about that is, I think the easiest way to do it is if you draw a diagram like this. You can break it up into like sort of legs of the journey. Each one of those legs, you just ignore what direction it's in, call it positive. So how far is the person gone? They've gone 10 meters from here to here, right? Plus 8 meters from here to here, plus 5 meters from here to here. So it's 10 plus 8 plus 5. And you can think of that as like the first leg plus the second leg plus the third leg. And that's equal to 23 meters. Any questions about that? Okay. So now the next thing we have to talk about, if we have the directional quantities and the non-directional quantities, we talked about position, we talked about displacement, and that's related to distance. And now we have to talk about velocity, which is related to speed. So we're here. Okay, so now velocity and speed. I'm going to talk about velocity in 2 steps. First, I'm going to define average velocity. And then I'm going to define instantaneous velocity. This is the only one that we care about. This is the one that we want, the useful one. But I have to define average velocity because we're going to use the idea of average velocity to define instantaneous velocity. Okay, so first, average velocity. And just like with displacement, average velocity only makes sense if you choose two different instants to look at, like an earlier and a later instant. So we'll choose two instants, T1 and T2. Then the average velocity is a fraction, and it's equal to the position at the later instant minus the position at the earlier instant divided by the elapsed time, T2 minus T1. And you could write that same thing with the function notation. So it's equal to the position at the time T2 minus the position at the time T1 divided by T2 minus T1. Okay, and on a position versus time graph, let's think about what this means. So you have time on the horizontal axis, position on the vertical axis, and let's say that the graph you're looking at is something like that. Okay. And let's say that our T1 is here, and so this would be our position P1. And let's say our T2 is here. So this is our T2, and then this would be our position P2. Can you follow what I'm drawing on here? Okay. So now, if you think about slope as being equal to rise over run, okay, the slope of a line is the rise over run. Think about the rise from this point to this point. It's just equal to P2 minus P1. And the run is just T2 minus T1. And so if you draw a line that goes from the spot on the graph at T1 to the spot on the graph at T2, okay, then the average velocity is the slope of that line. V average is slope of that line. Yes? Yes, it does not go where I drew it. Dang it. Thank you. It goes from, so it needs to go like that. Any questions about that? Okay. Um, and if that average velocity, okay, so velocity is always directional. It always has directional information attached. And that direction is the sign, the plus minus sign. So if you have a positive average velocity, that means that the line between the 2 points that you're looking at is tipped counterclockwise from the horizontal. If the average velocity is 0, that means that that line is horizontal. And if it's negative, that means that it's tipped clockwise from horizontal. Based on that formula, what would you expect the units of velocity to be? So, yeah, it's a kind of length over a time in whatever system of units you're in. And then the SI units are meters per second. That's right. So the units for velocity are length over time. And so the SI units, meters per second. Okay, so your car, now we're going back and forth between velocity and speed, but imagine you paid extra for a car that gave you the velocity instead of the speed, so it had minus sign. Anyways, either way, your speedometer tells you you want to know your speed or your velocity at a single instant, right? The average velocity, to define the average velocity, we had to choose two different instants, right? We had to choose a T1 and a T2. And, that doesn't really go along with, like, when you're in your car, you don't look at your speedometer and define two different instants. You just want the one speed that represents right now, And so how do we go from this average velocity that requires two different choices of instant to an instantaneous velocity that the idea is only represents a single instant? That's what we're trying to do. You see so average velocity, you need to choose two instants. Instantaneous, we want something where we can just choose one. So how do you do that? So now we're going to talk about instantaneous velocity. So now we're just going to choose a single time t. And the way you figure out what the instantaneous velocity is at that single time t is, I'm going to do it in, I guess I'll write it as 2 steps. So step 1. Based on your single time t, choose a t1 smaller than t and a t2 larger than t. and record, notice what you get for the average velocity. Okay, so it doesn't matter what those two values are, but you have one on one side of t and one on the other side, and those two values, now you calculate the average velocity and you write it down. And now step 2, you choose t1 and t2 a little bit closer to that value t that where you want the instantaneous velocity. So choose t1 closer to t and a t2, I guess closer. And calculate that average velocity. And then these steps go on, really they go on infinitely many times. So this is not a good way to calculate this exactly, But that's the idea. Yes? Oh, yeah.
Yeah. So let's say like the first one.
Mhm.
So like 0 seconds,
Mhm.
so on. Would it be best to go from like E minus A to C?
For this step process, let me do an actual example, and I think it'll make more sense when I do that. It's kind of abstract still, But the idea is, like, once you go through all these steps, continue doing this. This list of average velocities that you'd get would get closer and closer to that v instantaneous. And exactly when you write down your infinite numbered average velocity, you'd be at the instantaneous velocity, which would never happen, obviously. Yes. It's a limit. That's right. So, right. So this is the idea of limits for the people who've had Calc 1 or seen that in like a pre-calc class. So let me do an example, and you'll sort of see how it works. So let's say that the function, the position function, is equal to 2t cubed. Okay. So what that says is, if you want to know what the position is at a given instant, you choose the time that you want. So let's say time equals 4 seconds. You plug 4 in for t. So 4 cubed is 64. And then 2 times 64 is 128. And so this says at time equals 4 seconds, the position is 128 meters. So that's how a position function works. Okay. And let's say that we want to calculate the instantaneous velocity at time equals 2 seconds. So step 1, I'm going to make my T1 1 second and my T2 3 seconds. Okay, so we have one of those on each side, one before and one after. And then the average velocity, those two choices of T1 and T2, would be 2 times 3 cubed minus 2 times 1 cubed divided by 3 minus 1. So that's 3 cubed is 27 times 2 is 54. 1 cubed is 1 times 2 is 2. 3 minus 1 is 2. So you have 52 divided by 2, so 26. So that's our first guess at the instantaneous velocity at time equals 2 seconds. And then our step 2. Now we still want our earlier instant to be a little before 2 seconds and our later instant to be a little after, but we want to pinch a little closer. So I'm going to say T1 is equal to 1.9 seconds, and T2 is equal to 2.1 seconds. And then for this step, our average velocity is 2 times 1.9 cubed minus 2 times 2.1. Nope, I have them backwards. 2 times 2.1 cubed minus 2 times 1.9 cubed divided by 2.1 minus 1.9. And that is about, so you get 18.522 minus 13.718 divided by 2.1 minus 1.9, and you get something like 24.02 meters per second. Yes. Yes, that's just what I specified for this problem. And that just has to do with what the motion looks like. You know, like if somebody's going, like if you go back to the example we did here, I didn't, so this is the bungee jumping one. I didn't give this as a mathematical function. I just gave some values and we sort of drew a line through it. But if you wanted to try to come up with a mathematical function that approximated that pretty well so you could do calculations, you know, you'd use some kind of cosine function, you know, where the amplitude of the cosine was decreasing over time. And you could use that to, you know, and once you knew that, you could go through all these mathematical steps that I'm doing now, you know. Okay, so 24.02. And now step 3. This is the last one I'm going to do. We have to pinch a little closer. So now I'm going to say T1 is equal to 1.99 seconds. T2 is equal to 2.01 seconds. And so the average velocity is 2 times 2.01 cubed minus 2 times 1.99 cubed divided by 2.01 minus 1.99. And for that one, you get about 24.0002 meters per second. And like I said, to do this, really, like, to follow this procedure to get an exact answer, you'd have to keep doing it forever, you know, so that's not going to work. But at least you can probably believe. So the answers were 26, 24.02, 24.0002. We did it again, we'd be even closer to 24. And it appears that we started somewhat near 24 and little by little are getting closer to it. And it turns out that 24 is the instantaneous velocity for this position function. So the instantaneous velocity at 2 seconds is 24 meters per second. That limiting process, coming up with a way to get a numeric value for a limiting process like that without doing infinitely many steps, is what Calc 1 is about. So anybody who's taken Calc 1, you know, you probably went through a very similar thing to that at some point. We're not going to do calculus in this class, so we're going to end up using formulas for instantaneous velocity that came from the calculus, but you don't have to do it. But this is the idea of, you know, this is my best, the best I can do to come up with like an intuitive idea of what instantaneous velocity means, you know. Okay, so notice, a couple things to notice. The first one is to calculate the instantaneous velocity exactly uses calculus. So if you're wondering where calculus comes into physics, this is the most important place where it does. Second thing is the absolute value the instantaneous velocity is the instantaneous speed. So if your speedometer says 55 miles per hour, then depending on what direction you're going, your velocity could be positive 55 miles per hour or negative 55 miles per hour. But it has to be the case that if you take the absolute value, it agrees with your speedometer. The sign of the instantaneous velocity, tells you which direction you're moving. Okay, so say that 35W, you decided that was going to be your one-dimensional path, okay, 35W. And you chose one, and it only goes north or south. I don't know which direction we're facing, but north or south, you know. And let's say you chose positive to be north and negative to be south. Okay. Then if you're headed from here towards Iowa, you're headed in the negative direction, and your speedometer says 55 miles an hour, what's your instantaneous velocity? So you're headed in the negative direction. Your instantaneous speed is 55 miles an hour, so your instantaneous velocity would be negative 55 miles an hour. And if you're on the same highway going north, now you're moving in the positive direction, so your instantaneous velocity would be positive 55 miles an hour. So if you know your instantaneous speed and you know which direction you're going, you can combine that into an instantaneous velocity. And the last thing I want to say, the last thing to notice is, since the instantaneous velocity is really, for the most part, the only kind of velocity we care about, is the most important type of velocity. Anytime you hear just velocity or see just v, so anytime you see velocity or v, that means instantaneous velocity. If there's a problem that wants you to calculate something about the average velocity, it'll say that specifically. Okay. Okay, so this gives us a way, if we're talking about instantaneous velocity, we know how to calculate the instantaneous speed. You just chop the sign off, whatever it is, and take the instantaneous, the absolute value. But there's one other thing that comes up in the problems that are assigned. That's the average speed. And the average speed is just the distance between the two instants divided by t2 minus t1. So the distance you traveled between t1 and t2 divided by the elapsed time. Okay, so yes. Mm-hmm. Yep.
Is it vital that T1 and T2 both be the exact same distance away from T to get the right answer?
It makes them converge to the right answer a little faster, but no, it's not. They can be different distances on the two sides.
For example,
right.
It wouldn't give you the wrong answer?
No. And, you know, this is really just, there are no problems I'm going to give you where you have to do this. It's really just a way, like if you're curious about where that idea of instantaneous velocity comes from, this is where it comes from. It's, and besides that, some people might be interested because this is also where calculus comes from, this way of thinking about it. So it's kind of an interesting mathematical idea, but I'm never going to make you go through multiple steps like that. All right, that's all with that. Any other questions about velocity or speed? Okay, the next thing we have to talk about, the last quantity that's going to be important to us with particle kinematics. So the last time you have to write this comparison thing, directional and non-directional. So we did position, we did displacement and its connection to distance. We did velocity and its connection to speed. And the last one we have to do is acceleration and its connection to what we think of as acceleration if something's speeding up and deceleration if something's slowing down. That's the last one. Okay, so let's say acceleration and then and speeding up and slowing down. So velocity told us how quickly an object's position was changing and in what direction it's changing. That's what velocity does. In the same way, so just as velocity tells us how quickly position is changing, acceleration tells us how quickly velocity is changing. So based on that, if you had this information sitting in front of you and your life depended on coming up with a definition for acceleration, you might think like, well, maybe it'll look like the same form as the definition of velocity. I'm just going to put the velocities in the place that the positions were in before, right? You might think that. If your life depended on it, you got to say something. Might as well say that. And that is how acceleration works. So acceleration. So choose two instants. T1 and T2. Then the acceleration is equal to the velocity at the later instant minus the velocity at the earlier instant divided by T2 minus T1. Or equivalently, you could think of it as the velocity as a function of t at that point t2 minus the velocity as a function t at t1 divided by t2 minus t1. And because of the similarity between this formula and the formula for velocity, you might also think like, hey, maybe there's average acceleration and instantaneous acceleration, and maybe and all that is totally true. There is average acceleration and instantaneous acceleration, and the way that you define instantaneous acceleration is doing a limit of the average accelerations, just like we did with velocities. We're just not going to have to worry about that in that class because the problems we do are going to have average constant acceleration. And since the acceleration is constant, it doesn't, instantaneous and average are the same thing. Okay, but so we won't have to worry about average versus instantaneous acceleration. But that is a thing. And these V1 and V2 in this acceleration formula, are those average or instantaneous velocities? Those are instantaneous because anytime I just refer to velocity, I mean instantaneous. Okay, if I ever mean average, I'll say average. One thing to notice, well, let's do two things. Okay, so notice. First one is for the acceleration to be equal to 0, what has to happen with the velocities? Constant. So the only way you can have acceleration equals 0 is for velocity to be constant. So you can think of those two as synonyms. A problem could say acceleration is 0, or it could say velocity is constant, and in both of those cases, you know acceleration is 0. And then the second thing, the units for acceleration are length over time squared. And so the SI units are meters per second squared. Any questions about that? Okay, let's stop there. And Wednesday, I still have a few things to say about acceleration. And then finally, we'll get to actual calculations where we're given information about a motion, and we'll have formulas that'll let us calculate the other quantities based on the ones we know.